All right, so everybody, hopefully you can see these are the instruction manuals, or at least part of the instruction manuals to Lord Business's evil lair. Okay? For those of you who have not seen the Lego movie, don't make any inferences that Lord Business is evil just because they call it the evil lair. So I'm going to be teaching a winter study course on the mathematics of Legos. One of the big points of this class is, in some sense, operations, research, and efficiency. So last year we tried, and some of you in here I know tried with me, to build the 3,152-piece Superstar Destroyer in 10 minutes or less. We just missed by 21 seconds. So we are going to be doing it again. What we need a few more people. That was the problem. And so if anybody is interested, you don't even have to take the winter study to just help out. We are going to be doing a practice and an advertisement. We're going to show the Lego movie on October 19th, 2:30 p.m. in Peresky in the 62 Center on stage. Anybody who wants to help build Evil Lair is welcome to do so. Kayla has set the rules. So the rules are, we have 11 minutes. She figured since we didn't quite do it in 10 minutes, she'd give us 1 extra minute. It's a smaller set. And we're not allowed to practice. But we are allowed to print out the instructions and try to figure out how we should break up the task efficiently. So if anybody is interested in helping do this as an extra credit project, by all means let me know. The other question is, I am talking with various people for jobs for you guys to do. Right now there's a real issue going on in Mount Greylock Regional High School. It serves several towns, and there's a real difficulty with people and after-school programs in getting the kids home safely. And so right now there's not enough money to have buses running all the time, and they are really looking for creative solutions to try to figure out when the buses should be running, where they should be running, how often they should be running, what time of day. If anybody is interested in something like that, please let me know. There are a lot of people. I was at the school committee meeting yesterday. There were a lot of parents who were appreciative of the efforts being done, but were very worried about the safeties of kids. Okay, so now going into class today, I apologize. We're actually not going to be doing general nonsense. We're actually going to be doing linear programming today. We're actually going to be doing operations research. All right, it's time to actually start the real part of the course. We're going to start solving real problems. All right, so by now, hopefully you've been motivated enough about thinking about these, and you've gotten enough of a sense of how to look at these things. What I want to do is talk about the diet problem. So this is one of the most important problems you could have. You know, if you become a dictator. I don't know if any of you are considering a career as a dictator. Depending on how well you do, you have job security. But what are your goals as a dictator? One thing is, you might want big monuments made to you, right? A lot of dictators seem to like that, at least in ancient times. Followers is good. So if your followers are dying, if they're too weak to build monuments, this is bad. So you want the people to be fed enough so that they can make big monuments to you and they don't die and they don't revolt. Okay? So this is going to lead us to the diet problem. What is the cheapest way to keep people alive? Because really, you don't want to be spending too much money on them. Okay? Now, I've got to be very careful not to make any comments about the dining halls here. I think the food is actually decent here compared to what I had as a student. But you may have more goals in life than just the cheapest possible diet, right? What else might you consider? Yes? Well, I will count nutrition as keeping you alive. So, you might consider variety, that you may not want to eat the same meal every single day. Somebody who ate peanut butter and jelly almost daily for 12 years, it's fine. Yes?
Quality.
Quality. So how good do things taste? So how much are you willing to trade between food that tastes good and food that's cheap? And this leads to multi-objective linear programming. So the first thing we're going to do is we're going to do single objective linear programming. We only care about one item, and for us that's going to be essentially cost. Later we will realize how absurd this is, and we will then care about several different things. And then it becomes an interesting challenge as to how do you take all these different concerns into play at the same time. There will be trade-offs, and you will have to come up with some kind of exchange rate. You've probably heard the phrase, you can't compare apples and oranges. You need some conversion factor. How many apples is an orange worth to you, and vice versa. And so if you have a diet that costs you $15 and tastes like crap, and a diet that costs $15.02 and tastes like a gourmet meal, typically that 2 cents is a good investment. If it costs an extra $2,000, well, if you're Oprah Winfrey, depending on where she is in her cycles, you may be able to easily pay that $2,000 to have that meal without really feeling the cost. But for most of us, that extra $2,000 would not be doable. And so it becomes a very serious issue. All right, so what I want to do is I want to talk a little bit about linear algebra first. So we're trying to solve AX equals B. So for the most part, this is not that hard to do. We have ways to do this. You might do Gaussian elimination. And as a nice exercise, try to see how fast is Gaussian elimination. If I give you a matrix A, how long is it going to take to read off B? And the whole idea of Gaussian elimination is we reduce A to a very nice form. If A is upper triangular, we can then just read off the answer going boom, 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 going all the way up. So we put the matrix in upper triangular form. You have to be a little bit careful about numerical stability maybe when you're doing some of these calculations. All right, what are the possible solutions for AX equals B? How many solutions can we have? Yes?
0, 1,
Okay, we can have 0, 1, or infinitely many solutions. What do you think is going to be the interesting case for us? 0, 1, or infinitely many? Infinitely many, right? The no solutions is not going to be too interesting. Typically, when you're doing optimization problems, some optimal strategy exists. And this is where you use something called abstract nonsense or advanced real analysis. You say, I've got some kind of compact space. I have some way of guaranteeing that as long as things are continuous, there will be a maximum, there will be a most efficient thing to do. There will also be a least efficient thing to do. Let's imagine you own a movie theater. What is your goal as the owner of a movie theater? Make money. Okay, you make money two ways. You show movies and you sell food. Okay, and you have to decide which is more profitable for you. And it might depend on the movie. And I've actually done work with the movie theaters. I'm happy to talk about this later in the semester. If you're George Lucas, you can put in a lot of constraints on somebody who wants to show The Phantom Menace because they don't know at first how bad it's going to be. They think, oh, it's been a long time. It's going to be a good Star Wars movie. It's going to be played for at least 6 to 8 weeks. It's going to be played on your best screens. You have to have a certain level of sound system. And you may be getting enough people coming in weeks 1 and 2 that this is a good deal, but by weeks 7 and 8, it may not be a good deal for you. So it becomes an interesting challenge. Then we have lots of constraints. You can't have 2 movies showing on the same screen at the same time. Is there a way to come up with a set of choices for which movie to show on which screen that will satisfy all the constraints? And I'm not telling you what the constraints are, but can you tell me something I can do that will satisfy all the constraints? Yes? Not show any movies. All right? You will satisfy all the managerial constraints. You won't have 2 movies showing at the same time because you won't have any movies showing at any time. So a lot of times you can prove a solution exists from very trivial ways. Okay, typically that's not what we want. We want an efficient solution. We want an optimal solution. So if we only are in a situation with 0 or 1 solutions, well, we get what we get. Typically there will be infinitely many solutions, and then you can put in secondary issues. I want to minimize costs. I want to maximize revenue. And I want to somehow search through the space. And so here, we could look at solving AX equals B. And if we have infinitely many, many solutions, choose the one that maximizes or minimizes C transpose X. So that'll be C1 X1 plus Cn Xn. So this is a linear condition, a linear cost function. Is there much of a difference between maximizing and minimizing? No. Okay. Now, yes, if you are working for a firm, there is a difference between, at the end of the day, maximizing their profit and minimizing their profit. Okay? If you understand the mathematical theory of maximization, you understand the mathematical theory of minimization. All you do is what? Yeah, just replace everything with a negative. So if I understand how to find the maximal solution, if I just replace C with negative C, if I find the maximal solution of that, that's finding the minimal solution of the original problem. So you get a choice of, do you want to maximize profit, do you want to minimize cost? Either one of these is perfectly acceptable. We will often adopt the point of view that we're trying to minimize cost, just for definiteness. And this is going to lead us eventually to what's called a canonical formulation of a linear programming problem. So you should have read this stuff in the book by now or the notes by now. I'm trying to give you an overview of where we're heading and why we're doing this. By choosing the standard set of notation, it just makes it a little bit easier to talk about what's going on. All right, so this is how linear algebra works. We have a matrix equation like this, and we have some kind of constraint, some kind of objective function here that we want to maximize or minimize. It turns out that once we put this in, this is now linear programming. Now initially when you see linear programming, you have a lot of inequalities. We'll see later that you can always remove the inequalities by just adding more variables. And this is again going to be searching for the canonical form. A linear programming problem is always going to look like this. So at this point, this is now linear programming. So in the diet problem, we're going to try to minimize cost subject to a diet that will keep us alive. Are there any conditions on the amounts of food we can buy? What are the conditions?
Well, you can't buy more food than is available.
Okay, one is you can't buy more food than is available. What else?
You have a budget.
Okay, you have a budget. What else?
Well, you can't buy enough food if you're going to stay alive.
Well, no, you would just die, but you could buy no food. It wouldn't be a feasible solution. You die. It's a little bit gross, but there's something you can't do.
Eat people.
I'm sorry?
Eat people.
Well, depending on what we define as food, you may be able to eat people. What can you say about the amounts of food I can buy? What kind of numbers are they? Yes. Positive or non-negative, okay? You are not allowed to buy negative amounts of food. I'll let you ponder what a negative purchase would mean. All right, we're not going to do something like that. So for linear programming, it's sometimes more than just you have an objective function like this. You often have constraints on the quantities you're studying. I'm only allowed to look at quantities that are non-negative. If you think back to maybe high school, you might have had some of these problems. You're trying to find the box that has maximum volume given certain constraints. And you sometimes get a quadratic equation because you've done some kind of squaring, and you throw away the negative solution because you're not going to have a box with a negative length. We will often have additional constraints like this. So in a linear programming problem, it's not just an objective function. It's also maybe the xi's are non-negative. Okay? So this is going to be the general framework. And I'll write this down again more carefully later. But I want you to see how it's flowing very naturally from linear algebra. Linear algebra solves ax equals b. What are we doing? We're tweaking it by saying, well, look, if we're in a situation where we have infinitely many solutions, we can now pick and choose among the solutions. We can look for the one that's best. Most of the time, we will be in an underdetermined system. If we're in an overdetermined system, there's at most one thing to do. It's really not that interesting. You know, in most situations, you're going to have multiple choices. Yes?
Say we like don't. Actually, never mind.
Okay. Glad to help. Yes.
Would it be possible to have a variable constraint, such as you reach like the limit of food, if the price increases exponentially?
So you can do stuff like that, but it may no longer be linear. So the key thing right now is this is a linear equation in my unknowns x's. This is a linear equation in my unknown x's. And so as soon as you leave linearity, things get much harder. Also right now, everything is real valued. So I'm assuming I can buy pi units of food. Anybody ever see Father of the Bride? Steve Martin movie? One of my favorite scenes in that is he goes a little crazy about the cost of the wedding, and he goes into the supermarket and he just loses it. And he's very upset that they sell hot dogs in different numbers than hot dog rolls. And so he starts opening up the hot dog rolls and removing the ones he doesn't need so that each bag of hot dog rolls now matches the hot dogs. Now, of course, you could just say, look for, least common multiple and do something like that, but he's not really thinking mathematically at this point. And so the store does not allow him to choose to buy a fractional amount of a bag of hot dogs, and he gets into trouble for this. We will assume things are continuous at this point, and we can buy any amount we want. Our variables are continuous. If you think about a lot of things in life are going to be continuous. If you're thinking about shipping oil between a refinery and a city, you're talking about shipping so much oil that a few drops here or there doesn't really matter, so you might as well just assume things are continuous. For other things, however, the discreteness really matters. Can you give me a situation where my variables will be discrete? Yes?
The number of oil tankers you want to use.
The number of oil tankers I'm going to use. I can't use half of an oil tanker. Okay, that would be bad. Okay? I can't show half of a movie or use half of a screen. Okay? So for a lot of things, you're stuck, or fly half of a plane. Okay? For a lot of things, it's a 0-1 decision. You either do it or you don't. This will lead to the subject of integer linear programming. Integer linear programming is significantly harder than linear programming. And in fact, we don't always have efficient ways to solve integer linear programming problems. And that's a huge area of research of trying to find best ways to do this. All right, let me do a quick calc review. So I have f on a compact set S. If you want, think I have some set S like this. How do I find where my function is largest or smallest? What do I do? What's the procedure? How do I find it? So how do I look for the maximum and minima? Okay, so one is I take the derivative. And where does the derivative help me? For which points? Okay, so interior extrema are where the gradient of f equals 0. And the reason is if the gradient of f is not 0, then I have some direction where my derivative is positive, and if I go in the opposite direction, I have a direction where the derivative is negative. So if the gradient is not 0 here, if I just go maybe in this direction, my function gets larger. If I go in the opposite direction, my function gets smaller. Okay, so in that situation, this is how we find interior maxima and minima. What else do we do? Yes?
Check the boundary.
Check the boundary. And how do we check the boundary? I'm sorry? So who remembers the word we're supposed to use here? Or the phrase? If you're in econ and you don't know this phrase, you're in trouble. How do we check the boundary? Is there anybody here who had me for Calc 3? Okay, good. So I can yell at other people as Calc 3 instructors. How do you check boundaries for extrema? Lagrange multipliers. Excellent. So exterior, so we'll say boundary. We do Lagrange multipliers. So the gradient of f is some multiple of the gradient of g. And so here, this is the constraint g of x equals c. And so if I'm at some point, I have the gradient of g is the normal to the surface. And imagine I'm at some point on the boundary, and the gradient of f is in this direction. So linear algebra is a prereq for this class. I'm going to magnify things a little bit over here. So here is gradient of g. Here is gradient of f. What I can do is I can write the gradient of f as something in the direction of the gradient of g and something perpendicular to the gradient of g. If the gradient of f is not entirely in the gradient of g, then if I look at the directional derivative in this direction, I stay on my surface, I'm tangent to the normal, and my value is going to be increasing. And if I go in the opposite direction, my value will be decreasing. And so if I move in this direction, my function gets larger. If I move in the opposite direction, my function gets smaller. So this is using the notion of a directional derivative. Okay? So the only chance I have if I want an extremum at the boundary is the gradient of f has to be in the same direction as the gradient of g. Does that force us to have a maximum or minimum?
Sorry, can you repeat that?
Sure. If the gradient of f is not in the same direction as the gradient of g, I have no chance of having a maximum or minimum there. If the gradient of f is pointing in like this, if I move in this direction, I get larger. If I move in the opposite direction, I get smaller. So the only chance I have for maximum or minimum is where the gradient of f is in the same direction as the gradient of g. So the two vectors have to be pointing in the same way. That's why I have gradient of f is some multiple of the gradient of g. They're in the same direction. If they're in the same direction, does that force me to have a maximum or a minimum? Or if you want, think back to calculus 1. If f prime is 0, do I have to have a maximum or a minimum? No, it's just a candidate. These are called candidate points. So in calc 1, the function you should always remember is f of x is x cubed. And so f prime of x is 3x squared. F prime of 0 is 0. F double prime of 0 is also 0. So in this case, the first derivative is 0. It's a critical point, but it's not a maximum or a minimum. It's just a candidate. Hopefully, there aren't too many candidates, and so it's not a bad deal to find all the candidates and then analyze them. Okay? All of this is going to pay huge dividends when we get to the diet problem. Right now, we're looking at how we optimize things in Calc 1, Calc 2, Calc 3. How many of you remember Lagrange multipliers? How many of you at least remember hearing the phrase Lagrange multipliers at some point? All right. We're not going to do too much with Lagrange multipliers in this class, but I just wanted this as a way. Notice how much harder it is in 2 dimensions or 3 dimensions to check the boundary than it is in 1 dimension. Do you have a 1-dimensional analog of Lagrange multipliers, or do you basically just say screw it? What do you do in 1 dimension? Yes? Check 2 points. Is it that bad to check 2 points? No. Is it worth developing this advanced theory to determine which of the 2 points you need to check? Not really. It's 2 points. It's not a big deal. You have infinitely many points on the boundary. Is it worth developing a theory to narrow down from infinitely many points to 3? Yes. So this is why Lagrange multipliers are worth studying. It makes the problem doable. Okay? It passes us from an infinite set to look at to a finite set to look at. Okay? So this is a brief review of optimization in 1 dimension, in 2 dimensions. Okay? This is Calc 1, Calc 2, Calc 3. There is one other point that I should mention about Lagrange multipliers that was probably not really described too much when you took Calc 3. So for those of you who remember Lagrange multipliers, I know this is a subset of the class. You had this condition that if the gradient of f is not 0, if the gradient of f has a component that's not in the same direction as the gradient of g, you're not at a extremum and you keep moving. Let's say you want to find a maximum. Which way should you move? So let's say I'm in this situation and I want to find where is f largest. How should I move?
The direction of the gradient along the constraint.
Almost always yes. At least locally, that's the best thing I can do. And if there's time later today, I will talk about situations where sometimes the best thing to do globally is not the best thing to do locally. But right now, if I'm at this point, well, let's see, my function is increasing in this direction. It's increasing the fastest in this direction. I've got to figure out which way to move. Why don't I move in the direction where the function is going, increasing the fastest, right? This is almost like the evil person with the candy pointing it at the kids. Okay, there could be dangers in doing something like that, but your gut instinct is this is the way to go. So Lagrange multipliers is actually more efficient than you might have realized. You can actually use this to get a kind of algorithm to tell you how to find where that maximum point is. So just on a theoretical perspective, it's just, well, you solve gradient of f equals lambda gradient of g. How many of you remember solving these equations? Okay, your professors probably spent a lot of time cookbooking the problems if they cared about you to make sure you could actually solve these equations. Typically, this is going to be very hard to solve, and you'll have to do some kind of numerical procedure to approximate the solutions. But Lagrange multipliers tells you which way to go. Yes?
We were saying about it being really complicated. Is that true in linear programming
in linear programming, it's going to be very similar to Lagrange multipliers in that there's going to be a way to move. And so Lagrange multipliers, the way you should look at it is it's a condition that tells you, am I at an extremum, yay or nay? And if you get a nay, it tells you move this way. It may not be the best thing to do. It's the best thing to do locally. So I can either go into the diet problem right now, or I can give you an example of something that's locally good but globally stupid. Any thoughts? I'm sorry? Okay. So this is an example of first loud voice wins. All right. So I will do this, and then we will go on and we will do the diet problem. So it's from a wonderful series of papers called Do Dogs Know Calculus? And so the dog's name is Elvis. His father/owner is, I think, Tim Pennings. He's a professor somewhere in Michigan, and his dog actually knows calculus. So imagine you're in the water. So because I can't draw, I will represent his dog Elvis by a point here. All right? And you are next to Elvis, and you throw a stick. And so you throw the stick right here. What does the dog do? I'm sorry? He goes to the stick. What if you throw the stick over here? What if I, trying to think who's a good pitcher on the Red Sox. That's not easy this year. What if I throw the stick all the way over here? He really wants the stick. What does he do? Oh, I throw it infinitely fast. So the stick immediately arrives over there. Or I'm hugging Elvis in the water. He's not allowed to start moving with one hand while I'm throwing the stick in the other. He's not allowed to start moving until the stick lands in the water. What does Elvis do? So one possibility is Elvis goes in a straight line to the stick. That would be the case if Elvis does not know calculus. Yes?
He goes on land.
How does he go on land?
Using calculus. Sort of diagonal.
So sort of diagonally. And Elvis actually takes a path like this. Elvis realizes that he can run faster on land than he can swim in the water. And it is worthwhile to spend a little bit of time getting to land. Now, do you want to run diagonally like this? Do you want to run straight down? Interesting calculus problem. Globally, this is the right thing to do. If the stick is really far away, this is a great thing to do. If the stick is really close, it's not. So there's a critical threshold at which point this kicks in. If you look at where you are, say, a second later, where is he closer to the stick? The top path or the bottom path? The top. So the distance to the stick got smaller more by going in this direction than going in that direction. The problem is, if you take as your strategy, I will always do what's locally best. So I will always do what is locally best. That doesn't sound like a horrible maxim for life. But it can lead you to suboptimal positions. So this will not get you to the global best. It will get you to a local best. So if you consider a whole slew of paths, well, not surprisingly, the straight line path is going to do better than all those other ones. Yes?
Is the space of these paths
Let me think. You can definitely set up into a situation where you're compact, because most of these paths you can immediately eliminate as being foolish. And so in fact, the only paths you really have to consider technically is you run straight to it, or you run down here at this point and then come up at another point. So really, you only have two parameters of where you hit and where you leave. So this is a general warning that as we're doing these algorithms, you could get stuck in a suboptimal outcome. And so when we're doing things like the simplex method, one of the dangers is we may not be doing the global best. We may be doing something that's locally best, and we want to make sure we end up at the end of the day at the place that's globally best. Okay, So this is enough motivation. This is enough review of background material. Let's do the diet problem. So I think there's a typo in my notes. I'm going to try to use the corrected number. Okay. So the diet problem. You know, when I taught this years ago, we made up foods. I don't really care about them. So we have cereal and we have steak. Cereal costs $20 per unit. Steak, amazingly, costs just $2 per unit. So there should be no danger of you thinking that these are real numbers. Okay, this gives you 30 units of iron, and it gives you 15 of protein. And this one gives you 5 units of iron and 10 of protein. Okay. So what I want to do is I want to live, okay? A little bit more. Live cheaply. So we assume you need 60 units of iron and 70 units of protein. So I want to write down all the constraints and figure out what's going on. So let's assume we buy x1 units of steak and x2 units of cereal. Right. Are we allowed to buy any amount of steak and cereal? Yes, okay, we're not going to get into trouble like Steve Martin did. We can buy any amount we want. Can somebody give me the condition so that I make sure I eat enough iron that I live? Yes?
30C plus 5S is greater than 60.
30,
C.
not C. 30 times what?
X2, X1.
30 times x1 plus 5 times x2 is greater than or equal to 60. Did I switch them? I'm sorry? Oh, sorry. X1 units of cereal and x2 units of steak. All right, so that will make sure I get enough iron. What's my next condition? Okay, 15x1, 10x2. All right, this is my protein. Any other conditions for this problem? Yes? X1 and x2 are greater than or equal to 0. We're not allowed to have negative amounts of food. And what is our goal? So we want to minimize cost. So minimize, and our cost is going to be 20x1 plus 2x2 subject to the following conditions. Okay? So this is the standard linear programming problem. I have some constraints that come from the problem. I have some constraints on the possible values of the variables. I have something I want to maximize or minimize. How many people are eagerly anticipating developing the theory of linear programming to solve this problem? One person. How many people think we do not need the advanced theory of linear programming to solve this problem? Okay, why don't we need linear programming? It's easy to do in your head. These are not arbitrary numbers. What's the solution? Steak, right? Lot of steak. Why? Well, 1 unit of steak is subsumed by 1 unit of cereal, but 2 units of steak, I've got more protein. By the time I get up to 10 units of steak, it's the same cost as 1 unit of cereal, and I've got 50 units of iron to 30 units. Would you ever buy cereal in this condition? No. So I've deliberately chosen this one, so the numbers are not reasonable here, so we can just quickly look at this and see what the answer is. What would we need to do to make this a reasonable problem? Yeah, one thing is to increase the cost of steak. Now, if we increase the cost of steak too much, then we just buy cereal. And if steak costs $2,000 a unit, we're not going to buy any steak. So what you can get from this is that as I vary the cost of steak, I should go from the all-steak diet to a mixed diet to eventually just a cereal diet. And similarly, as I vary these other quantities over here, that should affect my solution. Okay? An interesting thing becomes what happens when these numbers are not known. So for those of you who are thinking of going off into various industries, you might want to hedge your bets. You might be playing the energy markets, and you don't know what the cost of energy is going to be. You might have different options. And so later we'll get to something called dynamic programming, where you don't necessarily know the values of these. Maybe there's going to be mad cow disease. Maybe the steak is going to become very expensive. But for now, we will assume perfect knowledge on the prices. And so now we're going to figure out how to solve this. Okay. So one of the maxims is always draw a picture. So solving diet problem. So here's x1, here's x2. Let's look at the first constraint. 30x1 plus 5x2 is greater than or equal to 60. Okay, so when x1 equals 2, I hit the x-axis. When x2 equals 12, so maybe 12 here, 2 here. So that's my line. Do I want the points above the line or the points below the line? Above. So if I put in 0, 0, if I put in some point in this region, I get no iron at all, I die. So anything above here is going to satisfy the iron constraint. Okay. Now I look at the second constraint. So this one over here, this was the 30x1 plus 5x2 equals 60. The next constraint is 15x1 plus 70x2 equals 70. So now what's the x2 intercept? 7, good, much lower. And the x1 intercept? A little bit more than 4, somewhere between 4 and 5. So let's see over here. And so now this would be the line 15x1 plus 10x2 equals 70. And again, anything above this line would be fine. Technically, I can extend these lines, and this would be valid. I'd be above all the different lines. Am I going to allow myself to choose this as a point? No. I also have the x-axis, the x1 axis. I have to have this thing over here. So I have to be above this. And I also have to be to the right of this one, x2. So at the end of the day, I see that even though this point over here satisfies the iron condition, it doesn't satisfy the protein condition. So these are not feasible. So this is the feasible diets. Any of these diets will keep you alive. Where do you think you want to be? Which intersection? So over here. So this is definitely a possibility. Where else might we want to be?
Kind of far from the lines.
I'm sorry?
Have a little breathing room for the lines so you're not going to die, like not on the edge of death.
You don't live until you're on the, no. We're going to live on the edge of death. That's fine. As long as we don't fall off. Yes. So one possibility is here. Are there any other candidates that you can think of? Yes.
One of the axes.
On one of the axes. And so the other thing is we could be on any of these lines. So what we get is we get a convex region. And we have 3 very special points. 3 is known as a finite number. Okay? And now let's really analyze what's going on. Our cost is 20x1 plus 2x2. Is that an upward sloping line or a downward sloping line? Let's see. What do you think? If I said 20x1 plus 2x2 equals 5, if I want to look at all diets that cost $5, is it upward sloping or downward sloping? Downward sloping. So again, because I don't really care, I'm going to just draw something like this. So maybe this is a cost of $5. And this is 20x1 plus 2x2 equals 5. So imagine I'm at some interior point. I'm on some cost line. And so my cost is $5. If I shift like this, if I shift my cost up to $6, that's just looking at a parallel line. So here, the cost maybe is now $6. And again, it may not be 6. I don't really care what the numbers are. So I guess just to make sure that I don't have to worry at all. I know that's far enough to keep me away from the axes. What if I shift inward a little bit? What happens to the cost? It goes down. So maybe here the cost is 4,000. So the first thing to note is we cannot have a maximum, we cannot have a minimum cost in the interior. So 1, minimum cost not in interior. That's really nice, because if we were at the interior, we can just take a parallel line that's closer to the boundary, and that will lower the cost. So we know immediately that the cost is not minimized in the interior. So we go from having infinitely many points to check to having infinitely many points to check. That's actually good progress. If we wanted to, we could actually check these infinitely many points without too much trouble. We could parameterize these things. We can use Calc 1 methods. But we know now it's got to be somewhere on the boundary. Okay? So now, does this look like anything we've seen earlier today? Have we seen anything earlier today that this kind of looks like? All right, so I'll let you look at what we've done earlier today to try to see a connection with some Lagrange, right? Trying to find some way to navigate the boundary. Now let's imagine we hit over here. I could flow in like this, and the cost goes down. So if I'm not at a vertex point, I could flow to a vertex point, and the cost would continue to shrink. Okay? And in some sense, this is almost like Lagrange telling us which direction to move. So if I landed over here, I know this can't be the minimum. I can always move in a little bit. What if I land over here now? Is that a minimum? Or what should I do? It's a candidate. Depending on what the slope of this line is, I might be able to continue to move. And now at this point, you would actually have to draw things well. If it's drawn like this, would I want to keep moving? Yes, I'd keep moving until I hit here. And then if I'm going like this, I would not want to continue any further. If instead the slope was like this, I would want to keep moving, and I would move to this point. So what you see is the minimum is at a vertex. There's one case I'm glossing over. What case am I glossing over? If the equicost lines, are you an econ major? Okay. You could be if you can use a word like equicost. So if the lines of equicost are parallel to these lines of constraint, we haven't handled that case. What do we do? Because then it's no longer the case that the minimum is one of the vertices. The minimum could be here. Pick a vertex. Right? So if the line of cost is exactly parallel to one of these lines, you're indifferent among these points. If you're indifferent among these points, let's get an algorithm that will terminate. Let's get an algorithm that will give you an answer. If you're indifferent among all the points, choose one. I hope my wife does not watch this video. When I'm often asked to provide feedback about certain purchases as to what looks nice, I often use whatever the second choice is. When I'm completely indifferent and I don't care, this way I provide an opinion and things progress. Okay? Please do not email my wife this, okay? So You need just some decision process. If you don't care among all of them, choose one of them. Does it matter which one you choose? No. Now, in real life, which do you think you would choose? The all cereal diet or the mixed cereal and steak diet? Probably, so, when you now have multiple objectives, the fact that you are now this region where you're indifferent, that's great. You can now easily factor in another condition that you want to optimize here. Okay, so this is essentially how linear programming works. For a lot of problems like this, we end up having a feasible region, which is in a huge, maybe, 10 billion dimensional space. It's convex. If you're ever at an interior point, you're not at a maximum. So you flow to the boundary. You land on a face. And if you're not at a vertex of the face, you can keep flowing until you get to a vertex. So instead of having infinitely many things to check, you only have to check the finite number of vertices generated by the intersections of the hyperplanes in your 10,000 dimensional space. Not bad, right? We've made the problem finite. Okay, according to my watch, let me just double check. Okay, I have that it's September. You agree? All right, so we've got a lot more time in the class. So we do not stop at, we've just made it finite, right? What's the theme of this class? Efficiency, right? Just because we've now reduced it to a finite calculation does not mean we've reduced it to a calculation we can do or want to do. We need a way to search these candidates. Is it hard to search the candidates here? No, there's 3 candidates. Is this a natural problem in the real world? No. Do you have more than 2 possible food choices? Yes. Do you have more than 2 possible nutrients you care about? Yes. So this is a very artificial problem. It illustrates the key features, but it's very artificial. We are going to need a way to quickly look from vertex to vertex to figure out where to go. So one of the reasons I did the Euclidean algorithm was because the idea behind that is essentially what we're going to be doing here. The Euclidean algorithm was wonderful, it was efficient, it moved a lot faster than you expected. We're going to develop something called the simplex method, which will tell us how to move from vertex to vertex. And it turns out it's a way to navigate all the vertices very efficiently, very quickly. Okay? You have no right to expect that something like that exists. You might have to just do things by brute force. If you look at integer programming, where now you have these 0, 1 decision variables. I show the movie, I don't. I fly the plane, I don't. I buy the product, I don't. We don't have good ways in general of solving these problems. We can, of course, solve them by brute force enumeration, but not in any reasonable amount of time for any problems we care about. All right, so this is the first of the real lectures in terms of what the class is going to be like. This is linear programming. This is the canonical example of a problem. There's other ones in the book. They talk about sending oil between refineries and cities. And so maybe we'll talk about that on Friday if you guys want to do another example. And then we will generalize and come up with a canonical form of linear programming problems. It allows us to put everything in the same framework. And because it's now in the same framework, we can use the same technique. In the old days when people solved equations, before we had this wonderful quadratic formulas and all this stuff, people often solved it differently depending on whether or not coefficients were positive or negative. They didn't like to have negative coefficients, so they might have x squared plus 3 equals 5x, because they wanted these things to represent positive quantities. And they would come up maybe with slightly different methods for each of these. Well, come on. Just put it in canonical form, ax squared plus bx plus c equals 0. You can attack them all the same way. That's what we're going to be doing. That's why we're going to spend so much time coming up with a canonical form. Okay. Then in terms of